Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Surface Area for a Solid of Revolution with Parametric Equations. As always, please be attentive while watching this video. By way of introduction, in this lecture we discuss how to find the surface area for a revolution solid of a parametric curve using only the parametric equations. And this is rather than eliminating the parameter and using the standard calculus techniques on the resulting algebraic equations. In science and engineering, important phenomena happen on the surface, and the magnitudes depend accordingly on the surface area, and often these are represented by parametric equations. So this is a core Calculus 2 course learning objective, but even more importantly, it can save you time when doing problems. And time, as you know, is precious. All right, so here we go. So in this section, we're going to rotate a parametric curve, and we're going to assume that it's given by, as we did in previous sections, x equal f of t and y is equal to g of t, and t runs from alpha to beta. And we're going to be rotating these about a coordinate axis, either the x or the y axis. So we're going to assume that the curve is traced out exactly once, as we always did. You could break it into different pieces if you needed to do something more than that. But only once as t increases from alpha to beta. At this point, there actually isn't much to do at all. You see, we know that the surface area can be found using one of two formulas, depending on the axis of revolution, and this was from a previous lecture just about surface areas. And recall there we had two formulas. The surface area, if we're rotating about the x-axis, is given by, and later on I'm going to call that S sub x in this lecture, but here I'm just saying it's about the x-axis, is the integral of 2 pi y ds, where s is the arc length parameter. And if you're not familiar with that lecture, you might want to go back and look at it again. But we did that before. We also found that this, and I later on will call this s sub y, is equal to the integral of 2 pi x, and again it is ds, where s is the arc length parameter. So in both cases, s is the arc length parameter. Now, these equations still apply, but instead of having a representation as we did earlier of y equal f of x, we now have a parameterization of x and y given by these functions of t, and x and y are separate functions of t. So that's what's new in this section. Again, here's the formulas that we're going to be using, but now the only thing we need to add is the formula from the lecture about finding arc length, where we found yet another expression for the arc length parameter ds. And so this is what we're using, and you might recall that in an earlier section we derived and used a formula called ds is equal to the square root of, this is dx dt whole squared, plus dy dt whole squared dt. And again, these are, what x is and y is in terms of f and t. And that's exactly what we need to do in the equation now. Now, as we had to be before, again, you will need to be careful with the x or y in the original formula. Back when we first looked at surface areas, we saw that sometimes, depending on whether you're using the dx or the dy, you had to substitute for the variable in the integral, and other times you didn't. That was dependent upon which ds formula we were using. And again, you could use either one. In this case, however, and this is good news, we always substitute for the variable. You see the ds here we use has parametric equations, and that's introducing a dt in the integral, and that means that everything you need to be in terms of t. Therefore, this is simpler. We will need to substitute the appropriate parametric equation for x and y depending on the axis of rotation. This is important, and it might have been hard to understand here, but the examples will make everything clear. Speaking of an example, here's your first example. I'm asking you to find the surface area of revolution of the solid created when parametric curve x equal 2t squared, y equal 2t cubed for t between 0 and 3 is rotated around the y-axis, and so this is the problem you need to do. Okay, it's useful for you to do this, and again, this is the kind of statement of a problem that I would give you on a serious assessment. So you know what to do. Let's see how you did. You don't have to graph it, but sometimes it's useful to graph it, so I did. So here is the, now this is in the XY plane, and you see that if I graph this for t going from 0 to 3, the y will go from 0 all the way up to, let's see, if I go to 3 cubed is 20, it goes up to 54. So you can see that this is what we're doing, and we're rotating it around this axis. And so this is a picture of taking that curve and rotating around the y-axis. And let's see, what else should I say? Oh, and what we're trying to do is we're trying to find how much paint do you need to paint the outside of this. What is the area of this thing? Not the volume, but the area. So we start with these parametric equations, which we were given, and we're going to call those f of t and g of t just to match up with our formulas from before. Okay, and so we'll need the derivatives of each of those. So f prime is 4t, g prime is 6t squared, and this, of course, is the formula because we're rotating about the the y axis. Okay, so we're just going to plug in. Now, what we're going to do is that this is going to be and now I am calling it sub y, just to remind myself we're going about the y-axis. This is the integral from 0 to 3, and this is 2 pi, and this is going to be, so there's the 2 pi, but here is x, and x, you remember, was f of t, that's in the previous slide, but that is 2c squared, and then what I'm going to do is square each of these derivatives and add them together. So I get this is the square, this is the ds parameter in parametric form. So this is 4t whole squared plus 6t squared whole squared dt. So I square that and I get this kind of an expression. 2 times 2 is 4, and so I get this, and so that's pretty straightforward. Now to do this integral, we're going to do some simplifications, and these will be useful. So first thing we're going to do is we're going to factor 4t squared out of here, and now I have the square root of 4t squared. But the square root of 4t squared is 2t, and it's actually 2 the absolute value of t, but t is positive as you go from 0 to 3. So I pull that out, and that is a 2t when I pull it out. And 2 times 4 is 8, pi is pi, and I have another t, so that is t squared. And what is left in here is the square root of 4 plus 9t squared dt. And let's see, so here I just am jerking the 8t through the integral. So that's what's happening there. Now you're confronted with this, and this could be a challenging thing, and in fact there's multiple ways to get the right answer. You could integrate by parts, or you could be clever with a substitution. And being integration by parts, I'm going to tell you, is more difficult, but I encourage the student to try that, and that should work, although it will take you a longer time to do it because you're going to be integrating by parts. Well, I think I actually could do it integrating parts by one time. But anyway, let's go ahead and talk about doing a clever substitution at this stage. So we're going to let u be 4 plus 9t squared, and that means that 9t squared is equal to u minus 4. This is a clever Calc 1 substitution. So you get u minus 4, that's just simplifying this, and that means that t squared is u minus 4 whole divided by 9. And that means that du going from up here is going to be 18t dt. And that means that dt equal du over 18t. Now, usually when I'm doing a definite integral, I'll deal with the limits, but I'm going to show you some. And by the way, that still would be my recommendation, although I'm going to show it a little bit differently here. Okay, so we do make that substitution. So remember from the previous page of notes, we had 8t, but now they're showing integrating, but they're being very careful to say these are integrals going from t equals 0 to t equal 3. I normally do not find my students being this careful, and so I'm not criticizing this this note because that's bad form, but you see you got a mix of u's and t's here, so you got to keep in mind that u is a function of t. So they don't change the limits of the integral, although you could, and if I were doing this problem by myself in some place, and I do math by myself, I would change these into u's. But here you'll see that this will work out all right. So anyway, we got this is the square root of u, there is dt, but now you got that t cubed. Now, what really happens, though, is that one of these t's down here will cancel with one of those t's, and you get t squared, and we already solved for t squared up here. So this is a clever Calc 1 substitution. So I'm going to say, oh, well, t squared was u minus 4 whole over 9. So this, I will call this u minus 4 whole over 9. And this is going to be the square root of u du. So now I have everything in u. And I would tell you that and by the way, we're pulling that 18 here out in front. So that's 8 over 18, and 8 over 18 is going to be 4 over 9 eventually. Actually, it could be 4 over 9 eventually anyway. But we have this. And you've got another 9 in here, so we're gonna pull that out in a bit too. Okay, so now this is an easy integral, and notice that they're still saying, but it's t going from 0 to 3. So that means they're not going to substitute until they do the u substitution. Then they're going to totally put it back in and do it. So again, it's not bad form, but that's not the way I would do it. Okay, so you distribute here, and you will get. Okay, so you will get. Let's see. Oh, we're still doing this. We're not distributing yet, but now we are distributing, and we get this. So this is the integral. So you end up with u to the 3/2 over 9 minus 4u to the 1/2 over 9 du. I do this term by term. These are actually easy integrals now. You add 1 to the exponent, and you divide by the new exponent. Well, I do that over here. And you're getting a whole bunch of things, and you then are evaluating this. Now, they're still got units of t, so we're going from 0 to 3. So you're not plugging that in yet. You have to. These are the t's. And again, if I had, if I were doing this on my own, I would have changed these limits and just plug it in, and I have my number already. But they have to back substitute because these are values of t. So this is 0 for 3. So we reverse these substitutions. And we get this, s of y is equal to 4 pi over 81. All of this business, you plug in 3 and 0. And if you simplify, you get that this answer is 4 pi over 81 times the whole of 39,950 times the square root of 85 plus 128 over 15. This is the exact answer, and that's what I would be looking for if you did this. Now, some of my students would say that's the ugliest damn number they've ever seen in their life, but I would remind them that there are no ugly numbers, just like there are no ugly babies. Here's another example, maybe more interesting for you to do. Determine the surface area of a solid obtained by rotating this parametric curve. This is x equal cosine cubed theta, y equals sine cubed theta, and theta is the parameter, and theta runs from 0 to pi over 2. You know what to do. Let's see how you did. You may want to sketch this. You could say, oh, when theta is equal to 0, this is equal to 1, and that's equal to 0. So 1, 0 is a point on the curve, and you could pick other points, but at pi over 2, this is 0 and this is 1. So you're up here on the axis, and so this, and connecting the dots and so on and so forth, this is the the curve you get. There actually is a name for this curve. It is called an asteroid, but that's a long story, and we're not doing that now. Okay, so let's go then. Well, we now have the parameters, so we need to get the derivatives. So dx d theta is, you got to use a chain rule. So this is 3 cosine theta whole squared times the derivative of u, and that's going to be minus sine theta. So you will, first of all, get this. So dx d theta is minus 3 cosine squared theta times sine theta. Similarly, dy d theta is going to be 3 sine theta whole squared times the derivative of the sine, which is the cosine, and that's what you get. And now that's what we have, but now let's get our formula for ds. Okay, so ds is going to be, and you should verify all this work, but I'm going to take dx d theta whole squared plus dy d theta whole squared. I'm integrating this d theta. Now, what happens here, there is a common factor of cosine squared theta, sine squared theta. So I factor that out underneath the square root, and then I pull it outside the square root, calling it 3 cosine theta sine theta. But now we have absolute values because the SIGN could matter times this, and so that's what we've got going on. But cosine squared theta plus sine squared theta is 1. So this really becomes 1. And on the interval that we're talking about, all trig functions are positive. That's in the first quadrant. That's convenient. That doesn't happen in real life, but it happens here because this is a sample problem. And so we get this is 3 cosine theta sine theta d theta. And here we're reminding ourselves we can drop the absolute value because both of those are positive in the first quadrant. Now this is the formula we need to use. S, on the previous example, I call that S sub y. Actually, I apologize. This is S sub x. We're rotating about the x-axis. That's why we're using this formula. But notice we take what we had for y. So y in this problem was sine cubed theta. And so we have 2y. This is sine cubed theta. And ds, we worked on that up here. And I substitute in. So this is the integral that we have to do. Now, what we're going to do is we're going to distribute, and we get sine to the 4th. Let's see. I take that 3 times that 2 pi to get 6 pi. And now I end up with sine cubed times sine is sine to the 4th. Cosine theta d theta, and this is a very nice substitution. I'm not going to go through the details. You should make sure you can do the details though, because on assessments I'm going to ask you to do that. But you can let u equal sine theta, so this is going to be u to the 4th du. And notice now that the limits do change because I'm integrating u, and I'm not saying t equals, so this is assumed to be du. So instead of going from 0 to pi over 2, now I'm going from 0 to 1. This is not hard to calculate. This integral here will be 1/5, and so you get 6 pi over 5. That is the exact answer. That's the answer I would expect you to share with me. Here's another problem for you to tackle. Let C be the arc of the circle. So here's the circle, but you're only talking about arc of it. The circle, though, is x squared plus y squared equals 9. And we're talking about going from 3, 0 to 3/2, this is 3 root 3 by 2. I'm not going to give you a picture. You'll want to figure that out. And find the area of the surface formed by revolving C. That's this arc of the circle about the x-axis. You know what to do. Let's see how you did. Okay, here's your picture of C. So there's C, that's the piece of that. And you know the equation of the circle, so that's good. And there's a picture of the C. We're going around the x-axis, so that's what we're getting. And again, we're finding the area of the surface. That means how much paint to paint the outside of it physically. Okay, so that's what we need to do. Well, this is important, or you could do it otherwise, but actually it's much easier this way. If you remember that the parameterization of a circle is done by, and in fact for this one, and it does matter where you're starting, but the parameterization here is going to be, this was covered in an earlier chapter lecture. This is x equal 3 cosine t, and y is equal to 3 sine t, and t runs from 0 to pi over 3. Because if I put t to be 0, I start here and I go up to there. Now for the answer, it really didn't matter where I start, but you can see that this does, and that helped us figure out the limits. Now there's some real work that was done here, but you should be able to do this. And let's see. Yeah, here they're saying, well, when x is equal to 3/2, you end up solving, and you know that t is pi over 3. Okay, so we just use our formula then. And so what we're going to do is this is going to be the integral of, this is going to be y because we're going on the x-axis, so that is, y was 3 sine of t. We're integrating from 0 to pi over 3, and there's the 2 pi. And then we have to plug in the derivative. So the derivative of this is going to be minus 3 sine of t whole squared. The derivative of this is going to be 3 cosine t whole squared, and we're good to go with that. Okay, now we start simplifying this. Each of those 3's gets squared. That makes that a 9. And then we have sine squared plus cosine squared. That's convenient. Doesn't always happen, but it happens several times it seems in this chapter. So we get 1 for that. So this is really the square root of 9, which is known to be 3. So this is a pretty simple integral. It is 3 sine t. I will expect you to finish the problem. So you find the antiderivative of this is going to be negative cosine of t. You see the minus sign we're pulling out here. We plug in the values. Make sure you can do this. But then we get a negative times negative is a positive, and we get that the area is 9 pi. Another example, and by the way, this example is significant because so many of your geometry problems, formulas, really come from calculus. For example, you might remember that, oh yes, in high school I remember that the surface area of a sphere of radius r is 4 pi r squared. But you might have wondered, I wonder where that comes from. Well, you're going to find out because I'm asking you to show that the surface area of a sphere of radius r is 4 pi r squared. You know what to do? Let's see how you did. Here's a picture of a sphere of radius r centered at 0, 0, and this is the formulas you're going to be using. By the way, here it's a little bit arbitrary what you rotate around what axis. You don't have to do it this way. You could have used x. You would get the same thing, but let's go through it. Again, the sphere is obtained by rotating the semicircle, and here I'm parameterizing it as x equal r cosine theta, y equal r sine theta, as t, it's not theta, sorry, is x equal r cosine t, y equal r sine t, and t runs from 0 to pi. Okay, so that will give you a parameterization of the top half of that sphere, and then if we revolve it at the top half of that circle, and if we revolve it around the x-axis, we'll be doing well on this. And so what we're going to be doing is we will go from 0 to pi. It's 2 pi. Y is being put here, and then I take the derivatives of each of these. The derivative of this is minus r sine theta. The derivative of this is r cosine theta. I square those and add them together. I get r squared. This is sine squared plus cosine squared. Yet again, is going to be 1. That doesn't always happen, but we're integrating r from 0 to pi. So what we're going to do is, and by the way, let's see. Okay, so and so r sine theta, but this, although sine squared theta plus cosine squared theta is 1, this is going to be the square root of r squared, which is another r dt. So you get r times r is r squared. And remember that we're integrating dt here. And so what I can do is I can pull out the r. It is a constant. So I get 2 pi r squared, and then I just do this integral. You should follow this calculation. The antiderivative of the sine of theta is the minus cosine theta. I plug in the numbers. Be careful about your SIGNs here, but you get that this is 4 pi r squared, which is what we were supposed to prove. Okay. Some reflections then. In the real world, where you'll spend much of your life, and you'll spend much of your life working in the real world, setting up an integral becomes a very important and an even more important skill. perhaps. Although the integral might be complicated and challenging to evaluate exactly, most of you will be scientists or engineers, and that makes numerical integration very important, because numerical integration, as you recall from an earlier lecture in this Calc 2 class, can allow you to find an approximation to an arbitrarily close tolerance. That means you can get an answer as close as you want by writing a little computer program or an Excel spreadsheet. Now, this can be sufficient to help you to buy enough paint to cover the surface area. Now, I put that in quotes because that's a little bit of a joke. I think that is a nice analogy of what you're really trying, but I will tell you that in your serious physics and engineering classes, it's not just about paint. And particularly in electricity and magnetism, surface phenomenon is extremely important. So, this is a big deal. Don't just think it's about buying paint. But I am going to say that paint is really fascinating. There's a lot of wonderful chemistry. They make paints now that allow you to do different surfaces. They're more durable, and you can paint in much lower temperatures now. And that's all due to some serious submolecular technology work that's going on here. If you were a chemical engineer, and this would be a good job working for a paint company in their R&D. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and each other. We're still in this together. May God bless you all.